Hello everyone, welcome to this week's lecture part 2. We're going to be talking about logistic regression. This is one of the most widely used tools in biostatistics and epidemiology. It's very similar to multiple linear regression that we saw a couple weeks ago, except now our response variable is categorical. So a quick outline for today, Gersman doesn't actually talk about logistic regression at all. So we have two other readings that are required readings. We have the PACE chapter and then Vidingoff, Glidden, Schabowski, and McCulloch, which they have a whole chapter on all kinds of advanced stuff. Just read section 5.1. That introduces logistic regression. I think the explanation that they give as to why logistic regression is a thing is much better than PACE. PACE just kind of states this is what we do, and you're kind of left with wondering, why do we do that? So I think the other reading is much better than that. I'm going to do an example. It's actually not from the book. It's a made-up example. But then we'll review our weekly assignments. So what is logistic regression? And again, it's very similar to multiple linear regression, except now our response variable is binary. So in biostatistics, one of the most common variables that we regress is survival and death. So what may cause death, for example? So does smoking mean that you are more likely to die or less likely to die, or whatever the case may be? And we try to model the probability of success. So now success, again, is in reference to our binary variable. A binary variable is any variable with two outcomes, again. That term, so the Bernoulli distribution or Bernoulli variable, it means the same thing. You have a variable with two outcomes, and one of them we're going to call a success, and we have a known probability of success. So basically, we're trying to model this probability of success. Um, so for example, if we say, if you have cancer, what's the probability that you survive? Well, that can depend on a lot of things, right? Maybe how old you are, whether or not you're a smoker, whether or not you drink, what treatment you're getting, how long you get it for. Maybe there's some other variables too. So we're going to try to model and estimate your probability of success. The equation that we do that now, we have our regression coefficients and our predictors, our x1, x2, I've thrown an interaction term here, but the probability of success would be e to all of this stuff, our regression coefficients, divided by 1 plus e to that same stuff. And this is not a linear model. Remember, when we talked about multiple linear regression, we said linear is in reference to the regression parameters. They have to be like separated from each other. You have to go like one regression parameter times a bunch of stuff, then plus the second regression parameter times a bunch of stuff. That's a linear combination. This is not a linear model. So we could use nonlinear regression methods to fit this model. And that's actually probably what I would do, just because it's easier to interpret when we're just talking about probabilities. That being said, the much more common method is logistic regression. What logistic regression is in order to get the right-hand side to look something like this, it looks exactly the same as the right-hand side when we did multiple linear regression, right? But in order to do that, we have to transform our variable. And the way that we transform it is by putting this function together. This is called the log odds function or the logit function. What this does, again, it's the probability of our success divided by 1 minus the probability of success. Now remember, 1 minus the probability of success is the probability of failing, right? So the probability of success divided by the probability of failing, that's what odds are. That's the definition for odds. So this is the odds of success, and we're taking the log, the natural log of odds, so log odds, the log odds transformation. And if we do that, then on the right-hand side, we get something that looks like something that we can do linear regression on. This is called a generalized linear model. The only difference between this and multiple linear regression is that there's a transformation here. We've transformed the response variable. Now, there are also implications on our error terms, but really, when I say generalized linear models, that's what it means. It means that the error terms are going to have some distribution, and it's going to vary. Our response variable might be transformed, but the regression parameters and the explanatory variables are always going to look something like this. That's a generalized linear model. So for multiple linear regression, the errors were normally distributed. There was no transformation. For logistic regression, we're using the log odds transformation, and the errors will follow binomial distribution, basically. Okay. Um, One thing to pay attention to is that these regression coefficients, we're regressing log odds. So not only is it odds, it's the logarithm of odds. So if I say, well, if our explanatory variable x1, maybe this is age or something, for every one one increase in age, so if you're 1 year older, then the log odds increases by 2.3. What the heck does that mean? I have no idea. I don't have an intuitive understanding of what log odds are. I would need to transform this back into probabilities. And so that's what you should do. And the way that we can do this is when we have our prediction, so we have our predicted log odds, that's essentially beta 0, beta null plus, that's all of this stuff. So we'll take E to our log odds divided by 1 plus E to our log odds. And that's what we'll do. And we'll do an example of this later. Again, what I want you to take away is logistic regression differs from multiple linear regression in 2 ways. One, we're applying this log odds transformation on our response variable because our response variable is a binary variable. It's yes or no. And the errors will follow a different distribution. Okay? So just like multiple linear regression, fitting this model assumes and forces this model and this structure onto the data. So be careful that you're not doing that inappropriately. That's kind of difficult. We're not going to really get into that so much. We're going to focus on interpreting model output today. If you take another statistics course, if you ever take a linear modeling course, for example, then they'll worry about all of that. And there's several other models that you're going to learn how to use and how to implement and how to decide which model is best. But again, the interpretation is what we're going to focus on. The method is least squares regression. That's the same for all of the generalized linear regression models. That being said, it's a little bit weird because of the transformations that we're applying. The assumptions are that the explanatory variables need to be mutually independent. That's the same. So we've got same multicollinearity problems that we need to worry about. The response variable follows the Bernoulli distribution. Again, this is basically a fancy word for saying that the response variable has 2 outcomes or is a binary outcome, yes or no. We're going to call one of them a success, and we need to know that probability. And then there also needs to be mutual independence across our entire sample. Okay? Now, we're estimating the probability, but the point is that there's a fixed probability. Now for residuals, there's a couple different ways to do this. And with logistic regression, there's something called deviance residuals. I'm not really going to get into it too much. The only reason I'm mentioning it is because in model selection, we calculate deviance residuals, and the probability, or as opposed to doing a t-test for our regression coefficients to see if our predictors were significant, this time it's a chi-square test on deviance residuals. Now the interpretation is the same. So even though the test is a little bit different, it works basically the same. And we'll see an example of this. Basically, each of our predictor variables, we're going to calculate this test statistic with deviance residuals. There's going to be a chi-square test and there's going to be a p-value. So in order to determine if our explanatory variable is a significant predictor, we're still looking for a p-value that's below 0.05. That's the same. Okay, just know that the test is a little bit different. So it's a lot of these little things that they're not little things, but these types of things that are different, but the interpretation stays the same. Just like, any statistical test, you have a null hypothesis, you have an alternate hypothesis, you have a p-value, and you interpret that p-value compared to your confidence level, right? That's the same on all tests. So that's the same on this test too. So we're, again, focusing on interpretation. So you'll see an example of this. Now, collinearity, I mentioned, interaction terms, indicator terms, model selection, they all work the same as in multiple linear regression. At the very least, they work the same in their interpretation. So diagnostics, the tools that we use are going to be slightly different. Because our response variable is binary, a good tool to use as opposed to a scatter plot of predicted values versus observed values is a box plot now, because a response variable is binary. It's either success or failure. So a box plot of our estimated probabilities, and they should be very different. Our estimated probabilities of success when a response is a success should all be very close to 1. And it should be the estimated probability should be very close to 0 when the outcome is 0. That's a perfect model, right? So there's going to be some variation there, but we want to see box plots that don't overlap. And we're going to do, we're going to do examples of all of this. And then we should also do scatter plots of estimated probabilities by our explanatory variables. Now, just a quick reminder that correlation is not causation. And so just because you fit a model and just because it's statistically significant and just because you've got significant predictors doesn't mean that you actually found a causal relationship between your explanatory variables and your response variable. They just happen to be correlated, okay? So that interpretation of causation is out of the hands of statistical tools. That requires a whole separate set of tools. And we've talked about this before, but just a friendly reminder to don't fall into that trap. So when we did multiple linear regression, I talked about a general regression procedure. So for logistic regression, this is the procedure. It's a little different. I cut out a couple steps, but you should be familiar with this by now. So I'm going to dive into our example. So we have data from a study that was done on the analgesic effects of treatments on elderly patients with neuralgia. So they're giving some anesthesia, 3 different kinds. One is a placebo, and then we have 2 different treatments, A or B. So the response variable is whether or not the patient is reporting pain. So pain is a response variable. Yes is like the success. So ideally, we want to figure out what reduces pain. It's a little bit backwards, but we have, again, yes or no, pain or no pain, and that's our response variable. We're trying to predict whether or not patients experience pain by what treatment they got. So there's 2 different treatments called treatment A and treatment B, as well as a placebo. And then we also have the patient's age, their sex, and the duration of the complaint before they were given treatment. Okay, so I want to do the following steps. So the first things first, it's what's the full model equation? We're going to do a logistic regression. So the full model equation, it's, well, pain is my response variable. Because this is a logistic regression, because pain is a binary variable, I'm going to do the log odds transformation. So my response looks like this. So the natural logarithm of pain, the probability that somebody is in pain divided by 1 minus the probability that they're in pain equals, we have our intercept term, then our predictors, our age and duration, they're both quantitative. Then we have sex. Sex is categorical, so I need an indicator variable. So I'm choosing as a reference group the males. So if you're female, then we'll have this other regression coefficient that we'll add on. If there's no difference between males and females, then this regression coefficient is not going to be statistically significant. Okay, but this is an indicator variable, and this is not the reference group, but this is if the sex equals female, then that's what the indicator's for. So it's 1 when you're female, it's 0 when you're a male. If you're a male, then the regression coefficient times 0 is 0. So males are kind of built in, that they're the reference group. Now, it doesn't really matter what you choose as reference group. You just need to choose 1, basically, and then make sure that you have your interpretation correct. And the other variable was treatment. Now, treatment, there were 3 different treatments, treatment A, treatment B, and treatment P for the placebo. So I just chose treatment A as my reference group. So I need 2 different indicators, 1 for treatment B, 1 for treatment P. Okay. Now, I didn't include any interactions in this model, but you certainly can. If when we're looking at the residuals, I see any patterns, then I certainly may come back and add some interactions. But there's a lot of variables here. So if I wanted to add all of the possible interactions right now, it's going to get a little bit complicated. So I'm just going to leave it with this simple logistic regression model, basically. Okay, so now let's look at some output and let's identify what the significant predictors are. Now I'm going to dive into here is Microsoft Word. This work has been done not in R like I've been doing all term, but in SAS, which is another software. SAS is not used in academia as much because it's extremely expensive. Academia pretty much uses R. The epidemiological world uses SPSS a lot, but if you start talking to some biostatisticians, they probably prefer SAS. SAS is used by a little bit more of your hardcore statistical people. You have a lot more flexibility in what you can do with SAS, but it requires you to know how to program. So SAS has a language and you have to learn how to program its procedures and et cetera, et cetera. So that's the type of places that you see SAS. Now, the output is going to look quite different, but we're still going to have p-values. We're still going to have coefficients. So I want to help you if you're starting to get familiar with R and the output that I'm generating in R. I want to try to show you what it's like to look at something else, but still be able to pull out what we need. Okay, so first thing, this is a scatter plot of age versus duration. This is just exploratory data analysis. It looks like there's 3 outliers over here where there's a couple of people that had to wait quite a long time. Most people looked like they waited at most for 30 minutes, but 3 poor souls had to wait somewhere between around 45 minutes. So that might be affecting some analysis. Remember, outliers are generally not good when we're doing regression. So maybe we should throw them away. For now, let's leave them in. Now we have our response variable pain. So no pain is on the left, yes pain is on the right by age. So it certainly looks like the elder persons experienced pain more often than younger persons. And now we have duration versus pain. So, and it certainly looks like people who experience pain did not have to wait as long. So that's good. Now, I would argue maybe even that duration before treatment is probably caused by whether or not you're experiencing pain. If you say, if your nurse comes over and you say, I'm in pain, I'm in pain, I'm in pain, and you are in real pain, then you're going to get treatment faster than if you're like, yeah, you know what, it's kind of annoying, but I can deal with it. Then they're going to go deal with, the patient who's in actual pain who can't help but feel the pain. So I don't know if this is necessarily appropriate to put on our model right now, but there certainly looks like there is a relationship. So let's keep that for now. And just for the sake of argument, we'll see what happens when we remove those outliers. Now, duration versus pain, those box plots almost completely overlap now. So I wouldn't be surprised if this is an insignificant predictor and this gets dropped. Age versus pain, this doesn't change too much. So I think that probably duration is not significant predictor in a model, that age probably is. And we don't see treatment. Well, this is the treatment. This table is a little bit difficult to read. Basically, this is the percentage of people not in pain. This is the percentage of people in pain by treatment. So 25% of the people on treatment A were in pain, 25% of people on treatment B were in pain, 75% of the people on treatment on the placebo were in pain. So it looks like the placebo doesn't work. A and B, there is literally no difference between the two of them in terms of the number of people who were in pain and were not in pain. So I think that there really is no difference between treatments A and B, but both of them have a huge difference between the placebo. The placebo looks like it doesn't work at all. So now let's also look at gender. It looks like 27% of the females were in pain compared to 57% of the males who were in pain. So it looks like there is an association between gender and the amount of pain. There is an association between whether or not you had the placebo or one of the other treatments, but there's no differentiation between treatment A and treatment B. It looks like duration is not related to pain. It looks like age is. So now my guess is what we're going to see is we're going to see a parsimonious model that includes age, that includes the treatment, but just the placebo. Remember, our reference group is treatment A. So B won't be significant, but a placebo should be. And if males is our which one of the genders is our reference group, then gender should also be, or sex should be significant as well. Okay, so that's our preliminary analysis. So now I think I have a pretty good idea. Here's some other stuff that doesn't really worry about us. Okay, so let's keep going to the part where, okay, here. So now what was typed in, it's a logistic procedure. So this is doing logistic regression. It's using backward elimination. So if you remember, I talked about the different selection methods. Backward elimination means that we're going to start with a full model that we discussed, and we'll remove variables that are insignificant one at a time. So we're starting with an intercept, treatment, sex, age, and duration. Okay. Now the first step, duration is removed. Remember, we said that it doesn't look like duration is significantly correlated. So that's been removed. And the p-value on the deviance residuals is 0.85. That's very not significant, right? P is much higher than 0.05. So then in step 2, nothing is changed. The p-value on each of the remaining 3 variables are all below 0.05. They're all pretty small. So treatment, sex, and age are all significant. So now it's going to estimate my parameters. So the intercept is minus 20.86. For treatment B, the p-value is 0.55. This is not significant. Remember, it's in reference to treatment A. And we saw this with the probabilities. Remember, 25% of people on treatment A experience pain, 25% of people on treatment B experience pain. So they didn't look like there was a difference. So compared to treatment A, treatment B is not a significant predictor of pain, a difference in pain. It doesn't matter if you're on treatment A or B. But the placebo is significant. So is sex, and so is age. So our final model is going to include the placebo compared to treatment A, sex, and age. So let's go write this right now, actually, in our PowerPoint slide. Let's write the final parsimonious model. Okay, so we have our intercept. The intercept is right here, minus 20.87. We're going to round it to a little bit. Age. Age is a significant predictor, so let's keep that. And the regression coefficient on age is 0.265. A duration was not significant, so we're going to remove that. Now, sex was, and it looks like actually female was the reference group. So I typed this incorrectly before. I apologize for that. So if you're a male, then the regression coefficient is 1.8235. Let's round that. Let's just keep it 1.82. Treatment B was not a significant predictor. There was no difference between treatment B and treatment A. Treatment P, on the other hand, was significant, and the regression coefficient there is 3.179. And so now this is our final parsimonious model. We have a significant intercept. We have a significant placebo effect, so an indicator for the placebo. Our reference group is treatment A. If you're on treatment B, there's no difference either. The sex is, we have female as a reference group, so if you're male, then this is the regression coefficient to increase the log odds, and age is also significant. So what this says, it's the older you are, for every 1 year older that you are, the log odds will increase by 0.265. If you're male, the log odds increases by 1.82, and if you're on the placebo, the log odds increases by 3.179. Now, what I would actually suggest, and I'm not going to go do this right now, but because we dropped treatment B as an effect, I would strongly consider redoing this model. and either combining the data from treatment A and B or making treatment P your reference group. This will average out the effects between treatment A and treatment B. Right now, this model is actually separating it. So we should combine those two groups if they're not statistically significant and then rerun the model and rerun the regression. And the reason we do this is, again, for categorical variables. We find no statistical difference between categories and we're using indicator variables. We need to combine them in order to make sure that our coefficients are not missing any effects, okay? But we're not going to do that for now. Let's leave it like this. Now, how do we, so we just kind of interpreted each of these regression coefficients, but changes in log odds are really difficult to understand. I don't know what that means. So let's convert log odds to probabilities. I'm going to retype everything, or at least just the regression coefficients. Okay, so here are our log odds changes. Now remember, I said that the way to convert it back was by saying changes in probability is E to the log odds divided by 1 plus E to the log odds. So the changes in probability are as such. But this is, you can't just do this already, because the probability is always between 0 and 1. If my probability of feeling pain was 0.5, and then you find out that I'm on the placebo, the probability isn't going to increase by 0.96, right? Let me do an example of this. So we set our function, let's go 0.25, 0.5, and 0.75. And let's calculate the probability. So if this was our log odds, then this is the log odds converted to probability, okay? And let's actually do one, let's do 1.25, 1.75, 2.25, 2.75. Let's just do those. So each of these are 0.5 apart, okay? So if the log odds increases by 0.5 between 1.25 and 1.75, the probability increases by 0.7. Now, if the log odds increases another 0.5, probability only increases by 0.05. And if it increases, the log odds increases by another 0.5, probability only increases by 0.35. So these were all equal increases in log odds. This was plus 0.5, plus 0.5, plus 0.5. But changes in log odds, changes in probability. So that interpretation is a little bit weird, okay? So we have to say if the probability of feeling pain is something, we have to start with something. So in this case, let's say if the probability of feeling pain is 0.5. Okay, now if the probability of feeling pain is 0.5, then what is the log odds? So this is going to be log of 0.5 divided by 0.5, and that's 0. That's perfect. So each of these is a change in the probability, given that the that the probability of feeling pain is 0.5. But we also have this intercept term. So really, this is our base. So the base probability is very close to 0. For every increase in age, you get a little bit more higher probability of feeling pain. But I know that this is confusing. I'm almost kind of confusing myself in how I'm trying to explain this. But I think the point that I'm trying to make is that interpretation is not straightforward. Log odds is really not an intuitive thing. You have to convert it into probability, and that is difficult to do. Okay, so really that's the takeaway. So if you're confused, good. That's the takeaway. It's just log odds is confusing. That's a great takeaway. Okay, just remember that you are in log odds and know how to calculate it into probability. So we're going to use this model to make a prediction, and we'll practice converting into probability in that sense. Okay, so before we do that, let's go back to here. So significant predictors. Our significant predictors were age, sex, and treatment. Point estimates for regression coefficients. We already kind of wrote that. That's here, these three numbers. These are our point estimates for the regression coefficients. And then let's make a prediction. So we have somebody who's 62 years old, is female, and received treatment B. Okay? So how do we do this? Well, let's remove all of this stuff. So we have somebody who is 62 years old. They are female, so they are not male, and they received treatment B, so they did not receive the placebo. So we take 62 times the regression coefficient. They're not male, so that times the regression coefficient is equal to 0. And they didn't take the placebo, so that times the regression coefficient is also going to equal 0. And we add it up with the intercept. So their predicted log odds is minus 4.4. Let's convert that to probability. The way that we do that is e to this number divided by 1 plus e to that number. So the probability that this person feels pain is 0.0116. 0.0116. Let's round it again. Let's do another one. Now we have somebody who's 73 years old. They are male, and they received treatment P, the placebo. Okay, this person now is 73. They are male, and they did receive the placebo. So again, we add everything up. So we have the intercept, age times how old they are, right? 0.265 times age plus 1.82 times yes, they are male times 3.17 times yes, they did receive the placebo. So we add all of them up, including the intercept, we get 3.474. E to 3.474 divided by 1 plus e to 3.474 is 0.9699. This person's probability of being in pain is 0.9699. Let's do one last one for good measure. Let's do a 68-year-old female who received the placebo. Okay, this person was 68, is not male, did receive the placebo. So we have the intercept minus 20.87 plus 0.265 times 68, that's 18, plus 1.82 times 0, they are not male, so 0, plus 3.179 times 1. Yes, they did receive the placebo. So all of that added up is 0.392, so the log odds is 0.392. E to the 0.392 divided by 1 plus e to the 329 is a predicted probability of pain equal to 0.5815. So hopefully that makes a little bit sense. I think plugging things in and multiplying them together, that's the same as multiple linear regression. The only difference is now we have to transform log odds into probability. Okay, that's very, very important. Don't leave it as log odds. If I tell you, oh, the log odds that you feel pain is 4.2, you're going to tell me, I don't know what that means. I don't care. I'm feeling pain. Once you convert that into probability and say, oh, the probability that you feel pain is 96%, you'll be like, yeah, I'm in pain. Good call. So that's much easier to interpret. Probabilities are much easier to interpret than log odds. So make sure that you transform back. Okay? So that's all for this lecture. Again, problem 6 covers material from part 1 of the lecture, chi-square, CMH test, et cetera, risk ratio, odds ratios, confidence intervals. Lecture 2 covers questions 7 through 10. We're talking about logistic regression, doing all the things that we just did. We're making predictions, we're interpreting the regression coefficients, we're identifying significant predictors, we are writing full models, and the equation for the models. We know how to look at statistical software and say, yes, this is a significant predictor because the p-value is low, or this isn't because the p-value is high. And that homework, this is the last homework of the semester, or the last problem set at least. That's due this week. Again, I know it's Thanksgiving, so have a wonderful Thanksgiving. Happy Thanksgiving. Please spend time with your family and friends. I don't expect you to do any work on Thursday or Friday or Wednesday, really. You're probably cooking. But please make sure to get a start on this problem set early, ask your questions early. You can put your questions about this material in discussion board 5 under week 14. Next week, we do have a quiz that's on this material. So it's on chapters 16, 17, 18, and 19. So this was the z-test for, or the hypothesis test for a significant difference in proportion, so the rate difference. We also did hypothesis tests and confidence intervals for the rate ratios. Remember the terms relative risk, remember the terms incidence, et cetera. Remember the rule of thumbs for rate ratios and rate difference and what is meaningfully significant. Then we did chi-square test. Remember the difference between Fisher's exact test versus chi-square test versus the continuity correction for chi-square. Then we did Cochrane mental Hensel test. The CMH test, remember what that is. Remember what its assumption is. Remember the Bartlett's test. For common odds ratios. And then we did logistic regression today. So remember the transformation function, the log odds. Remember that the interaction terms are all the same. So if you have any questions, please put that in discussion board 5. Our quiz is next week. That's the last quiz. And then we have our final project coming up. So that's all for this week. Again, if you have any questions, please let me know via email or in the discussion board. Just a quick review today. We just talked about logistic regression. We covered some of the things that are discussed in the PACE book and the Vittingoff, Glidden, Chabowski, and McCullough readings. We did a quick example, not from the book. I showed you some output from SAS, which looks a bit different. But that being said, we should be able to still pull out everything that we need to do. I realize I didn't go through some of the diagnostics, so let's do that really quickly now. So we have, let's change the view here. Oh, no, I like this better. Okay, so this is a box plot of the predicted probabilities against the response variable. So here is people who did experience pain and a box plot of the estimated probabilities. And if the model was perfect, everybody would have a predicted probability of 1. And now here are people with no pain and estimated probabilities. And again, if it was perfect, people would be down here. But we're looking for good separation between these box plots. And indeed, the box plots look very separate. The main box down here is quite low, which is good. The main box for people who did experience pain is quite high. So that's exactly what we wanted to see. Now the residual plots, or the deviance residuals, let's zoom in a little bit for this. This is residuals by observation. And there's really no pattern here versus predicted probability. Basically, we're looking for two parallel lines or parallel things, and that's good. We kind of see that. There might be some curvature here, which means that we might need to do an adjustment. For the most part, it's pretty straight. That's good. Again, for residuals versus age, this looks like a big score, but it's really not. There's actually a separation right here. So we have one line here and one line here. It looks like the variances change a little bit. So there might be some problems there, but it looks If we fitted lines to this, this looks like they're going to end up with two parallel lines. For the treatment, we have two groups. We have one group up here that looks relatively straight and another group here. The placebo was quite different. So at the very least between treatment A and B, that looks like there's no huge difference. And for sex, it's kind of difficult to see, but the residuals don't look too much more spread out for any one sex compared to the other. So it looks like for the most part, we don't have anything that are glaring violations of the model assumptions. So that's okay. Again, our parsimonies model kept treatment, age, and sex. Okay, so that's all for this week. Be sure to watch part 1 of the lecture. Have a wonderful Thanksgiving again, and I will see you after the break.